Hello students, welcome to Vista's Learning. This is Shruti, your chemistry tutor. As we already know, we have started with the structure of atom. This is our chapter. And we have already finished 7 sessions and this is the 8th lecturing class. Students, always we need to have a connection between the classes. So if you have missed anything, you can get back to Vista's Learning, and we are on online platform as well as we have the web application which is www.v-learning.in. If you missed anything, you can get back to the Vista's Learning, and we are here to help you, guide you, and studies will be easier with Vista's Learning. Getting back, as I said, we are in 8th lecturing class. This is what we are studying now, the energy. Energies of the orbits or orbitals. How to know about the energies of orbit? As we know, already have stated that we have the nucleus. As we already have the nucleus, around that we have the orbits, right? These orbits which is closer will have the lower energy, and while going away will have the larger energy. That is what we have studied, right students? So these have different energy levels. Likewise, we also have the energy levels for the orbitals or sub levels or sub orbitals. You can say S, P, D, F. If you see this S, P, D, F and so on, they are the orbitals. Even these orbitals will have different energy levels. So that is what we are studying now. If you have the different orbits with different energies, and also if you have different orbitals with different energies, how to distribute the electrons. So if you see here, the energy of the orbitals increases. How does it increases? It increases from 1s to 4f. So you can understand this is how the energy is. 1s means the electron is in the first shell. First shell is which one? This K shell, as we know. So the first shell we have s orbital, and this orbital will be filled first, and that is the first least energy. And then the second orbit which is having 2s. 2s means 2 gives you the principal quantum number which tells which is the orbit the electron is entering into. And 2s, s is the orbital which is been in second orbit. And we also have 2p there. That is equal to 2p. What they have given? Equal to 2p. That means the p orbital is also in second orbit. So here 2s is equals to 2p they have given. The next one is the 3s. The third orbit if I take, here also I have s orbital, and this third orbit which is having the s orbital will be greater than that of 2p and 2s. And this will be equal to 3p and 3d because it will be present in third orbit itself. Are you getting this point? So the 1s which is present in the first orbit will be of least energy level, and the second you will be having 2s and 2p, and the third you will be having 3s, 3p, 3d. Likewise, in 4p, in fourth orbit you will be having 4s, 4p, 4d and 4f, where you can see here. Getting this point? What does this mean? The energy of the orbitals also increases as the principal quantum number increase. The next point is the shape of 2s and 2p orbitals are different. An element or an electron has the same energy when it is in 2s orbital when it is in 2p orbital. That means if you have the 2s and 2p orbital, s is different orbital, p is different orbital, but even though they are in same orbit, same principal quantum number, which we can say 2 represents the principal quantum number here, where it is the second orbit, and in second orbit we have s orbital, p orbital. S orbital is having different shape, p orbital is also having different shape. We have already studied in last session, right? Do you remember that? Then good. So s and p have different shape, but still if they are in same orbit, they are having the similar energy. The orbitals having the same energy are called degenerate. What do they call it as? We call it as degenerate. The energies which are having the orbitals which are having same energies, then we call them as degenerate. So likewise, the first, even if you take d orbital also, in d orbital if it is 3d, 3p, 3s, they are almost of same energy. So the first 1s orbital in hydrogen atom corresponds to the most stable condition and is called ground state. What is exactly the ground state here? If the nucleus is present and the one which is nearest to the nucleus will give the first orbit, that is the K shell. And in this K shell, if you have the electrons, they are very, very ground state. We call them as ground state because they are almost in the stable condition, because they are very near to the nucleus and the attraction between the electron and the nucleus will be very high. So they are almost stable, and that can be called as ground state. So you can also take, if electrons are present in the first orbit, we can call them as they are in ground state. An electron residing in this orbital is most strongly held by nucleus. As I said, they are very near to the nucleus. So when the distance is less, the attraction will be more. When the attraction is more, then they cannot easily escape. So the stability will be more. Like it will be called as stable condition, but it is hydrogen is not having the more stable atom, but the electrons which are present in one s orbital will be called as stable condition, and we call it as ground state. And that ground state can be easily attained because of the attraction of nucleus towards that electron. Next, you have an electron in 2s, 2p or higher orbitals in hydrogen atom. If you take, we call it as excited state. Why do we call them as excited state? If you have the nucleus, you have the first 1s orbital here, so one electron will be here. If I take the second orbit, then this is 2s, it will jump to 2s. That means it is from first quantum to the second quantum, it is exciting, it is jumping. So we call this is the ground state for hydrogen atom, the electron in the hydrogen atom, and this is the excited state for electron in the hydrogen atom. Good. Next, the energy of an electron in multi-electron atom, unlike that of the hydrogen atom, it depends not only on its principal quantum number but also the azimuthal quantum number. Why like this? If we consider the hydrogen atom, then the energy level was depending on if it is 1s, it is lesser than that of 2s, and it is equal to 2p, and this is lesser than that of 3s, which is equal to 3p and 3d, and so on. Right, this is for hydrogen like atom. Why it is for hydrogen-like atom? Because they have one electron and it is easier, like one electron, number of electrons will be less, or nearly one electron system. So it will be easier for them to manage this quantum numbers. But here, if you have multi-electron atoms, like as we know carbon and more, then the crowd will be more. The nucleus cannot have the same attraction towards the first orbit and the higher orbits. So what is the difference here is that the energy of an electron in multi-electron atom will not only depend on the quantum number, but here it also depends on the azimuthal quantum number. What do you mean by azimuthal quantum number? Which gives you the orbital. As we know, azimuthal quantum number says either it is S or P or D or F orbital. So here also we have this azimuthal quantum number, which plays an important role to define about the energy of an electron in multi-electron atom. The main reason for having different energies of the subshells is mutually repulsion among the electrons in multi-electron atom. What is this point means? If you have the electron, what happens here? If you have two electrons, then this is a smaller radius, so it is sufficient for the electron to hold two electrons. And if you have the electrons here, these electrons will be repelling. They repel each other. When they are repelling, then the attraction will decrease. So here that also depends on the azimuthal quantum number and this difference, or why do they differ in the orbitals in the same orbit. If they are different orbitals, why they have the different in energy levels? Because of shape and also mutual repulsion among the electrons present in the same orbit. So the only electrical interaction present in the hydrogen atom is between nucleus and the electron. So there is no repulsion in between any other electrons, because there is no any other electron than that of one. So that one electron will be attracted by the nucleus, and that will give you this energy levels. Like it will not depend on azimuthal quantum number, and there is no repulsion between electron repulsion. There is only one electrical attraction between nucleus and the electron in the first orbit. Understood? Good. So next we are speaking about the interactions of an electron increases with increase of positively charged particle. And how does it increase? What is Ze? That is the number of protons present in the nucleus. That charge will increase, means the attraction towards the orbit also increases. Like orbit can be attracted by the nucleus. As the number of charge in the nucleus increases, the charge is increasing, the attraction towards the nucleus also increases. Understood? This is called as the attractive interaction between the electron and the nucleus. So that depends on the positively charged particle which is present in the nucleus. Due to the presence of electrons in the inner shells, as you have the electrons in the inside shell, so nucleus cannot reach exactly to the outermost shell. That will be crowded. For example, if I take the person who is sitting at the last bench and the person sitting at the first bench, what happens if the teacher is teaching in the class? They can easily hear, but by the time it reaches here, it will be low, right? Because distance matters. So likewise, here also, if the distance is increasing, what happens? The person, like it will be crowded. If they are crowded, and also these people may make noise and it will not be heard for the other or last person. Similarly, like nucleus will be having the attraction and if it is been crowded, the electrons are more, as we know, in between it increases, right? As the orbitals increases, the number of electrons also increases, and the positive charge increases. If the positive charge keep on increasing, electrons also increases, because number of electrons is equal to number of protons. So as it increases, if I have one electron in the last orbit, then the attraction between this and the first one is more, okay, than that of this, than that of third orbit, and the last orbit will not have exactly the same attraction from the nucleus. It will be less, because these electrons which are in between will be crowding, or they will be overlapping here, and the nucleus cannot get the attraction for the last orbit. Understood? Due to the presence of electrons, these electrons in the inner shells, the electron in the outer shell will not experience the full positive charge. That is important. It cannot experience complete charge or positive attraction from the nucleus what it is getting. Understood? And what is this called as? This is known as shielding. Shielding means which we are covering, okay? We are covering, the inner shells are covering such that the full attraction from the nucleus is not gained by the last electron in the outermost shell. So this is known as shielding of outer shell electrons from the nucleus by inner shell electrons. So we have the nucleus, we have the inner shell electrons here, and here we have the outermost electron, such that it is not getting complete attraction from the nucleus to this outermost orbit because of presence of inner shell electrons. What it is called as I said, it is called as shielding effect. The next one is the net positive charge experienced by the outer electrons is known as the effective nuclear charge. That means the full charge we have in the nucleus, we have full charge, and this full charge is not experienced by the electron. If I take the electron, this is not experiencing the complete full charge what the nucleus is having. It's because some of the inner shell electrons are attracted and it got less. The attraction towards the outermost electron will be reduced, and that reduction, after that reduction, what is the exact attraction the electron is tearing or it is been getting from the nucleus will be called as effective nuclear charge. So the attraction from the nucleus to the outermost shell after shielding, how much it is getting, that is called as effective nuclear charge. Hope you understand this. So you can easily say the net positive charge experienced by the outermost electron is called as effective nuclear charge. The next one is that we have, as we know, the s orbital electron will be more tightly bound to the nucleus than the p orbital. Fine. The s orbital electron will be more tightly bound to the nucleus than p orbital electrons, which in turn will be better tightly bound to the d orbital electrons. I'll repeat it. When you have the s orbital electron, than that it will be more tightly bound in p, and than that the p orbital, than that of the p orbital in d orbital, it will be more tightly bound. Are you getting this point? I'll say you. If you have the s orbital, in s orbital electrons are more tightly bound. In s orbital, the electrons are more tightly bound than that of p orbital, and the electrons in the p orbital are more tightly bound than that of d orbital. So in s orbital, electrons are tightly bound in that p orbital and than that of d orbital. So what is the increasing order? First s orbital more tightly bound, and then p, and then d. Understood? Good. So next we have, since the extent of the shielding from the nucleus is different for different electrons, then it leads to the splitting of energy levels within the same shell. So if I say you, I have s orbital, p orbital, as I said, s, p and d orbital we have. This is of same shell. Okay, s is of same shell, p is of same shell. If I take, I'll take it as 3 3 3. Okay, 3s because they all are in third orbit. Okay, so 3s, 3p, 3d, they are in same shell. And if I take this, since the extent of shielding is for the different orbitals in different electrons in different orbitals, that means the electron, if I say, if it is present in s orbit, p orbit, and then d orbit, if I say. So if this is the s orbit, which is having 2 electrons, p and d, now the electrons present in the s orbit will experience less shielding effect than that of p orbit and than that of d orbit. So that is what you can say, since the extent of this shielding from the nucleus is different for the electrons in different orbitals. So what happens? This split. So the energy levels will get split. So s will be here somewhere, p and d. So in the same orbit, the splitting will take place. So you can see here, the lower the value of n plus L for an orbital. I repeat, lower the value of n plus L for an orbital, the lower is its energy. Fine. So if you have n plus L, which is less, if we have n plus L of an orbital is less, then the energy is also less. If two orbitals have the same value of n plus L, the orbital the orbital with lower value of n will have the lower energy. That means if I take two examples, like 2 plus 1 fine. So if I take 2 plus 1, so n gives you the quantum number 2 and L gives you the azimuthal quantum number 1. So if I take 2 plus 1, it is equals to 3. And if I take the n value, which is 2 plus 1, but here we don't have 1 in this, so I'll take like 1 plus 0 gives you 1, and 1, 2 plus 0 gives you 2, and 1 plus 3 plus 0, 2 plus 1. So here, if you take like this, that means the third orbit, this is the third orbit, and as the shell, we have an electron that gives you n plus L orbit, and the second orbit and p orbital if you have, then that gives you the 3, n plus 1, n plus 1. Now what is the thing is that either the n is different, L is different, the n plus L, this is the quantum number n, this is the quantum number L, this is the quantum number n, the quantum number L. So what they are saying is that the lower the value of n plus L, if we have this number, when we calculate n plus L, for example, if I take for 3 plus 2 or 3 plus 1, that gives you 5. Then the 5 is greater. So if it is greater, then the energy will be more. If it is lesser compared to that of 3 and 5, this is lesser. So n plus L value is lower here, so energy will be less than that of the first one. But if it has the same n plus 1 value, for this also we have 3 plus 0 which gives you 3, 2 plus 1 which gives you 3. So if both are same lower energy, like same level, then which will be having the less energy, which will be having the greater energy, we need to know. So for that we have here n value. This n value gives you the principal quantum number 3. So this is in third orbit, whereas here it is in second orbit. By this you will understand, if it is in third orbit, or n is equals to 3 and here n is equals to 2, then which is greater here? N is equals to 3 is greater. So that will be having the more value, and one which is having least n plus 1 value, if you have similar n plus 1 value in that which is having the lesser n value, that will be having the lower energy. Fine. Energies of the orbitals in the same subshells. If I have same subshell, and how does the orbitals will be having the energy? And you can see here, energies of the orbitals in the same subshell decreases with increase in atomic number. For example, I am taking different atoms. They all have same third shell. So I am taking third shell of two different atoms A and B. So here the same subshell they have, for example 3p I'll take, 3p of A, 3p of B. In these two, the same subshells, they are of same subshells, which is having more energy, which is having lesser energy, we need to know. So energies of the orbitals is in the same subshells decreases with increase in atomic number. That means if I say atomic number of A is 43 and B is 50. So which is having the more atomic number? 53. So 53 will be having the least energy, whereas the 43 will be having the higher energy. I repeat, energy of the orbitals in the same shells like 3p, 3p, okay, the subshells is 3p, 3p. Thus, if I take two different atoms, then it will be having the lesser energy. Which will have lesser energy among A and B? It will be A, because increase in the atomic size. Like if the atomic size of B is increasing, so the atomic number is increasing here for B. As the atomic number is increasing, B will have the least energy than that of A. I repeat it. If I have A and B with 50 as the atomic number, this has 43 as the atomic number, I have 3s, I'll take 3s itself now, 3s and 3s for B. Both are in third orbit, both are of same subshells. Here what happens, if the atomic number is increasing, then the subshell will get lesser energy level. So this will have least energy level than that of A. Understood? Good. So you can see here the 2s of hydrogen atom, 2s of lithium atom, 2s of sodium atom, 2s of potassium atom. As we know, lithium, hydrogen is having 1 as atomic number. Hydrogen has 1 as atomic number, lithium has 3, sodium has 11 and potassium has 19. So what happens, as the atomic number is increasing, they all have the same energy like orbitals, same orbital, s orbital, then same orbit, second orbit, and the energy of these second orbit and the s orbital will be decreasing as the increase of the atomic number. Understood? Good. So now we'll study how to fill the orbitals. You understood the level, energy levels, right? The first thing is that if you have the less energy of n, like less number of quantum number, the principal quantum number n is having the least energy, then that will be having the lower energy level. We understood that. Then SPDF, S is having less energy, F is having higher energy. And we also understood if it is having the more atomic number, then the s orbital or same subshell of the given atom will be decreasing. Understood? Good. We'll just discuss how to fill the how to fill the orbitals in an atom. To know this, we have particular principles. So it is very much important to know these principles, how to give the place for electrons, or how to distribute the electrons or arrange the electrons in the orbitals. As we know, the energy is very much important to distribute the electrons. First, we have to fill the least or lower energies, and then we have to go for the higher energies. So we'll go with the first principle. This is Aufbau principle, where we say that in the ground state of the atom, the orbitals are filled in the order of their increasing energies. This is very much important. Why do we study about the energies right now? We studied about the energies to know how to distribute the electrons. It is based on energy levels, and if you know the lower energy level and the higher energy level, then you can fill the electrons likewise. So Aufbau principle says that in the ground state of any of the atom, the electrons will be filled according to their increasing energy levels. Likewise, 1s, 2s, then 2p, then 3s. Why first? Why we are not giving equal sign here? If you say 2s and 2p, they both are in same orbit. But as we discussed, other than hydrogen atom, the s and p orbital or multi-electron orbitals will be having different orbitals, electrons in their orbitals. So here the energy differs. Why does the energy differs? As we studied, as we know multi-electron atoms, the subshells will have different energies. S will have least energy, P will have higher energy than S. So first 1s will be filled, the first orbital and orbit, and then 2s, the first orbital of second orbit, and 2p, the second orbital of second orbit. Likewise, 3s, 3p, and then 4s, 3d, and so on. Thus, 4s and 3d will discuss this later. So next we also have one more principle which says about like Pauli's exclusion principle. What does the Pauli say? So no two electrons can be present or will have all the four set of quantum numbers. What are the quantum numbers we have? The principal quantum number, azimuthal quantum number, magnetic quantum number, and spin quantum number. You can also take it as MS. So all these four will not be same for any of the two electrons. That means each electron has their own unique address. Got it? Only two electrons may exist in the same orbital, but they will be having opposite spin. As I said, they may have the two electrons may have same principal quantum number, azimuthal quantum number, and also magnetic quantum number, but spin will be different. The spin might be plus half for one electron, and for other electron it will be minus half. So the maximum number of electrons in the shell with principal quantum number n will be given by 2n square. As we have already discussed this in the first chapter, you can remember this 2n square. How many electrons will be fit into the orbit? It will be given by this 2n square. The first orbit will be having 2 electrons. The second orbit will be having 2 2s are 4, 4 2s are 8 electrons. Likewise, you can calculate. Here we have the method how to follow this. So if you see here, you will be having the 1s, 2s, how they have been given here. So this is the first orbit. So this is the first orbit. This is second, third, fourth, fifth, and so on. So the energy levels will be given. First S will come, then 2S, then 2P, 3S, then 3P, 4S, then 3D, 4P, 5S. Then we get 4D, 5P, 6S. So this is the way we give the energy level or we distribute it. Coming with the last rule, that is Hund's rule. Hund's rules of maximum multiplicity. What does it say? Pairing of electron in the orbital belonging to the same subshell like S, P, D or F does not take place until each orbital belonging to the subshell has got one electron each. That is, it is singly occupied. I'll say you, if you have the p orbital, we have s orbit which is having only one different like a degeneration here. So it will just occupy one orbit. Whereas in p we have 3, it should occupy all the 3 sublevels with one electron each, then only it will go with pairing. Likewise, in d orbital also we have 5 where each electron will be singly occupied, then it gets paired up. This is what the Hund's rule says. For example, if I have d orbital or p orbital, I will take, if I have 4 electrons, the 4 electrons will not directly pair like this and leave the last one as empty. No, it is not possible. First, it should fill each orbital, one each, and then the 4th orbit comes and pairs the first orbit. Understood? Good. So next, electronic configuration, how to give it? The distribution of electrons into the energy levels or the orbitals will be called as electronic configuration, and it is different for different atoms, as we can also give this and represent in 2 ways. You have SPDF notations, like how I said, like 1s, 1s2, 2s2, 2p. Likewise, you can say according to the SPDF notation, or we can also show this in the orbital diagram. Just now, as I said, s orbital and p orbital, likewise you can show in the orbital wise also. Next, the electronic configuration of hydrogen atom is 1s1. Likewise, you have for lithium 1s2, 2s1. The electron in the completely filled shells are known as core shells, which is been completely filled inside, it will be called as core shell. And the electrons that are added at the outer shell will be giving you the highest principal quantum number, which is called as valence shell. You can also say the electrons present in the outermost shell will be called as valence shell. Whereas if I take the nucleus, we have the electrons here in the inside the orbits, that will be called as core electrons, and the outermost electron will be called as valence electrons. Next, you have here the examples where chromium and copper have filled with the electrons, 5 electrons and the 10 electrons in 3D orbitals. Rather than the 4 and 9, they have got 5 and 10. Why? Because their positions, like they have the electrons which is being fully filled and halfly filled. This is very much important. How to do this? We'll see it here. So reason for this fully filled orbitals and the half filled orbitals will have extra stability. If the orbital is having 4 electrons, like 2 electron here with 1 more electron, if you have, this is called as halfly filled. This will be having more stability than that of the half filled or the unhalf filled electrons. So you can say the fully filled or half filled orbitals will have more extra stability. So you can see here 3p or 3,6, 5d, like 510, F7 or F14 will be having more stability than P2 and P5 likewise. So this is your periodic table, students. The first gives you the s orbital, this is the d orbital, and we have the p orbital and f orbital which is been given here. These are separated according to the SPDF subshells. We'll discuss why it is been given like this in the higher class, like next classes, in the next chapter where we are studying about the elements and the properties. So here we have what is the utility of knowing electronic configuration. So if you see, the modern approach of chemistry is depending on entirely the electronic distribution to understand the chemical behavior of any of the elements. Because if you know the electronic configuration, you can understand either it is a metal or a non-metal or a metalloid, and how fast it is reacting or how slowly it will react. That can be given by that. And what is this? This is very much important. As I said, the stability of half filled and the completely filled orbitals, they are having the symmetry which leads to the stability. As I said, if you have the symmetry, the equality, then what happens? Stability will increase. And the orbitals in which the subshells is exactly half filled or completely filled are more stable because symmetrical distribution of electrons. They will be easily or same way it will be distributed with same distance. So it will give you the symmetry which leads to the stability. And then the electron which are in the degenerate orbitals have parallel spin and they tend to exchange their positions. When they are tending to change the positions, then what happens? The stability will increase. More number the exchange takes place, more will be the stability. So exchange energy is nothing but the energy released during the process. And the orbital are half filled or completely filled, then the energy exchanges is maximum. If the maximum exchange is done, then the stability will be more. Yes, students, by this you can understand about this. We Vista's Learning give you the quality education for all, and we work for right to quality education for all. For all the other videos, if you are missed, you can browse in into www.v-learning.in. Thank you.